let me start by repeating kind of where we come from. Okay, so the starting point which we had was we saying we have atoms which consist of nuclei, electrons around them, they come together, we would like to understand their structure. Okay? Then we have said, okay, we can write easily the equation which governs everything. And we made our first approximation, which was everything is non-relativistic. So we've written a non-relativistic Schrödinger equation, and it was a Schrödinger equation for a wave function of electrons and nuclei together, and there were all these different terms: kinetic energy of nuclei, kinetic energy of electrons, interactions between electrons, between nuclei and electrons and nuclei. So the equation looked quite easy. Then in the second step we said, okay, we would not like to deal with electrons and nuclei on the same footing. What distinguishes them is that on one hand, electrons are identical particles among themselves, so they have special rules, so we would like to treat them in a special way with respect to the nuclei. Moreover, the nuclei having a much, much larger mass, they are likely to behave more classically than the electrons, which will behave more quantum mechanically. So our game, or our aim, was to separate the two problems. The separation we achieved with the Born-Oppenheimer approximation, which we have done last time. Okay? So again, the Born-Oppenheimer approximation does not mean that we treat nuclei classically, but it means that we make a separation of the wave function, not a perfect separation, but a separation in the wave function in the precise way which we've done last time, and we ended up having two Schrödinger-like equations, one for a nuclear wave function, one for an electronic wave function. Okay? These two equations are coupled because in the Schrödinger equation for the nuclei appears a potential energy term, which I call U, and that U depends on the solution for the electronic problem. So the two are coupled, but nevertheless there are two different kinds of equations. Okay? So I've also said that this fact that you have a nuclear Schrödinger equation where electrons kind of appear only implicitly in a potential, this is the key element for doing classical simulations. So people use or invent a shape of this U, like Lennard-Jones and so on, which can depend also on angles or distances, all kinds of things, where without solving any electronic problem, one has an effective interaction, and then one only has to treat nuclei and electrons have disappeared. And this is a big success. While in this class, which is electronic structure, we would like now to see how we can solve the electronic equation. Okay? So the electronic equation, I remind you, was kinetic energy of the electrons, the interaction of the electrons with the nuclei, but the nuclei are now not quantum particles, they are just an external potential for the electrons. So they are 1 over distance from well-defined nuclear positions. Okay? So we have kinetic energy of the electrons, we have interaction with the nuclei, and we have interactions between the electrons. Okay? So, and then we said, okay, now let's look at the electronic wave function, which depends on all these degrees of freedom. And the point where we stopped last time is saying we have discovered the shape or a generally allowed wave function, and that was a determinant. Okay? Now, I will not write the whole determinant now again, but just, for example, for the case of two electrons, such a Slater determinant has a particular easy form, so phi, in this case it will depend on x1 and x2, because you have only 2. Okay. In this case, so it is, remember, 1 over square root of n factorial, so it's 1 over square root of 2. And then we have a determinant of a matrix which looks like phi 1 of x1, phi 2, phi 1 x2, phi 2 of x1, phi 2 x2, and the determinant of a 2 by 2 matrix is so easy that even I can write it. It's simply this times this minus this times this. So it is simply what we would have expected, 1 over square root of 2, phi 1 of x1 times phi 2 of x2 minus phi 1 of x, right, like this, phi 2 of x1 times phi 1 of x. Okay, so it is simply a product of single particle wave functions, but then there are plus and minus, and in this case it's the one where you exchange the two particles in the two. So this is a typical shape of a letter determinant, and you can have as large determinants as you want, as many electrons as you want. I've written last time how such a determinant looks like. And just to get used to how one manipulates a determinant, let us calculate, for example, the norm of a determinant. Because obviously what we would like to have is that phi times phi is always 1. We want normalized many-body wave functions. So let's calculate this. So we would have to calculate an integral phi star of x1 up to xn times phi of x1 up to xn, and integrate over all the degrees of freedom. dx1, dx2, this is, as always, the definition of a scalar product between these two. And now we say this is a Slater determinant and this is a Slater determinant. So we obtain 1 over square root of n factorial from one determinant, 1 over square root of n factorial from the other determinant. So we have 1 over n factorial. Then you remember every determinant has the sum over all permutations. Like here we have the permutation 1, 2, and then we have with the minus sign the opposite permutation 2, 1. Okay? So we have the sum over permutations. P, this sum comes from this determinant. You have another determinant where you have also a sum over all permutations. Let me call that P prime. So you have a double sum over all possible permutations. Then we have the sign in front of it. Minus 1 to the power p times minus 1 to the power p prime. So the sign here is the reason why here we have a minus sign. Okay? And this is what guarantees our fermionic sign rules, because we want, if you exchange x1, x2, to get the other sign. So again, this notation means you get a minus sign if the permutation is odd, you get a plus sign if it's an even permutation. So you have this here, and then now you have all these integrals. So you have this here multiplied with integral d3x1, and on x1 we have phi p of 1 of x1 complex conjugate phi p prime of 1 x1. Okay, so you integrate over the coordinate x1 like you integrate over all coordinates. In the first determinant with the complex conjugate, we have first the single particle orbital, which is at the first place in the permutation. Here we have the single particle orbital, which is in the first place in the p prime permutation. So you integrate over this. Then you have this times integral dx2 phi p of 2 of x2 complex conjugate phi p prime of 2 x2. Again, you have this integral. And in this way you have all n integrals times n. You have phi star, the permutation in the nth place of xn times phi permutation prime of n. Okay. So you have all these n integrals, and each one you see appears a scalar product between single particle wave functions. But obviously, as always, we choose single particle wave functions such that phi I, phi j is delta ij. So we have orthonormal single particle wave function. And what does this mean for us? Well, this means here, this here can be different from 0 only if this and this are the same single particle wave function. In the same way, this here is different from 0 only if these are the same, and so on. So this here tells us that we must have p of 1 is P prime of 1. So the two permutations must be such that in the first position we have the same index. The index does not need to be 1, but it must be the same index. Here we see that P of 2 is P prime of 2. Again, this tells us something about the relationship between the two permutations, because it means that in the second position of permutation P, we must have the same number as at the second position of the permutation P2, as P prime, sorry. And this here is again P in the F position is P prime. So what does this mean?
This means that not everything survives, only certain terms survives.
Okay, only certain terms survive, and which in particular?
So
what does this tell us about the two permutations? We have two permutations, P and P prime. We sum over all possibilities.
Must be exactly the same.
Exactly. So P and P prime must be the same permutation. Okay? Because if they differ somehow, then in some position there would be a different number and the integral gives you 0. Okay? So therefore we know that P and P prime must be the same permutation. So, meaning P is equal to P prime. Now this here is nice now, because you have all these things here. You know P is the same permutation as P prime, so one of the two sums goes away. So what is left here? This here is 1 over n factorial. Only one sum, say the 1 over P, remains because P prime is the same. The two minus signs, they go away, okay? Because minus 1, this can be plus or minus 1, but you have it squared, so this is always plus 1, so 1. And then here, all these terms, if the two permutations are the same, they are all 1. So you are summing over all permutations the number 1.
that is 1.
No, this is not 1.
N factorial.
That is n factorial. How many permutations are there? There are n factorial permutations. So n factorial permutations divided by n factorial is 1, as you say, right? So, therefore, our Slater determinant is the normalized waveform. Okay. So, we now know Slater determinants are very nice because A, they are always normalized, and B, they have the right symmetries. But I've mentioned last time already, they are also not good enough because they are not the most general wave function which is normalized and which has the right symmetries. In fact, a sum of several Slater determinants also has all these nice properties. So, it will not be good enough to look just for one Slater determinant. So, in order to understand better how many Slater determinants we have, we should now, as a next step, have a little closer look at these single particle wave functions. These ones here, the single particle wave functions, which are the building block for a Slater determinant. You always take n of them, bunch them together in a determinant, and you have a valid wave function. But how do they look? What are they? And this is what comes next. So we now come in big steps towards how one represents these things in a computer. Can I cancel it? You have copied it. We have to talk about representing orbitals or wave functions if you want, and operators in a computer. And the key concept which I will now introduce is the one of basis sets. Okay. So in order to make, as I just said, to create a letter determinant, we will have to understand what this phi I of r can be. Okay? Phi I of r is a valid wave function for one single particle everywhere in space. And then if you tell, moreover, if this is has this shape in space, if it's spin up, then we write it of phi I of x, but so the orbital becomes a spin orbital. But generally it's simply a wave function for a single particle defined everywhere in space. And the way one writes this typically is as a linear combination alpha ci alpha of d alpha of r. Now what is this? This is a linear combination, okay? A sum. These here are complex numbers, so complex number. Or if you want expansion coefficient of the function I amongst these functions b. And these b alphas, these are basis functions. The idea behind these is that one chooses a set of basis functions, and the basis functions, we will now give some examples in a minute, they are very easy functions. For example, it might just be sine x everywhere in space, or it might be e to the minus something. So some very easy analytically known functions are these here. And then you say every one of our single particle orbitals is a linear combination of those. Okay? And if you have many, many, many of those, all linearly independent, if they are very general, then you will be able to describe any shape of this function by combining those functions. So, but I will now give you examples of what one chooses as basis functions. But this is the way how you represent in a computer wave functions. Because in the computer can store only numbers, obviously. Okay? So before you start now, I want to write a computer program which does electronic structure. The first thing you must decide is in which basis function space do I want to work. You can, for example, decide to choose I don't know, functions which look like sinus n times x. Okay, sin x, they are everywhere, very easy. And then you write a computer program which uses that basis set. And all the computer needs to store for a given function are the expansion conditions. So this here is what you will always store in the computer. This here, because they are analytically known, the programmer must know, okay, these numbers refer to expansions of these easy functions. So, and in fact, what distinguishes, there are many computer programs, some are more used by physicists, some are more used by chemists, some are more better used for surface calculation, some better for molecules and so on. But what really distinguishes the programs which can do in a computer an electronic structure program is which basis functions are chosen. So this is kind of the first and most important choice, because all the programming and implementation of a computer code depends very much on how one can handle these functions. So let me say a little bit more. What can these functions be? So basis functions, and we have many possibilities of those. Many possibilities. Okay. And we will now say so. So one possibility as basis functions is we say that these b alpha of r we can choose as the subfunction phi l m of r minus r I. So what do I mean with this here? We could choose atomic basis functions. Centered at the atoms. And these atoms' positions, they are precisely like these. So this is what you have learned, for example, when you solve the hydrogen atom in the quantum mechanics course. You learn that there's a 1s wave function, 2s, 2p, 3s, 3p, 3d. So it has these kind of quantum numbers. And the idea is we could write all our single particle orbitals into which we put our electrons. We could write them as linear combinations of such atom-like functions centered at each atom. So for example, you have a molecule. Say, imagine you have a CO2 molecule, you have OCO, and on the oxygen here you put as basis functions a whole set of 1s, 2s, 2p, and so on functions. The same on carbon and on the other oxygen. And then you say the wave functions in the molecule, they will be linear combinations of those functions. The advantage is that this gives you very clearly kind of a physical picture of what is happening. If you know an electron is in a function which looks very much like the carbon 1s wave function, then you know from chemical intuition, this is it. Or if you see, I don't know, this is a linear combination mainly of the carbon 2p and the oxygen 2p, then you know, this might be a pi bond, as a chemist would say. So it gives you very clearly a chemical intuition of how the electronic structure and the wave function change by going from an atom towards an atom which has neighbors in a molecule. So this is something which is very, very intuitive and therefore also very useful. It has a lot of popularity. Anyone knows how this is called, this kind of approach? It has a name which some of you have certainly already heard, LCAO. So this means linear combination, because we write everything as linear combinations, as we've seen. Linear combination of atomic orbitals. So in this case here, the index alpha, over which you have alpha kind of with an index of which atom you mean, and of L and N, the quantum numbers of the atomic wave functions. Good. Great. So R, I, the index of the atom, L and N, and it's localized where the atom I is. So this is LCAO. It is used. There are many programs which do this. Sorry. Then there's another possibility. You can choose your basis function as, how did I call it? G ILM of R minus Ri. So also this here is a function which is localized at the positions of your atom. And these G's here, the G, I, L, M, are Gaussian basis functions. So what a Gaussian function? You probably all know what they look like. So a G, I, L, M of R is in fact something R to the power L, but then e to the minus alpha times R squared with some spherical harmonic L m of theta and phi. So, these functions, so the key, they are called Gaussians because they have this Gaussian shape, e to the minus a constant times r squared. Okay? So it's a function which looks, if you have r, it goes like this, and then it goes to 0. Okay? So you can imagine that this might be also something which looks like atomic wave functions. It has also the kind of like these here, the angular shape of an S or a P shape, whatever. But the radial part of the wave function, instead of being what an atom has, it has the shape of a Gaussian. This is by far the most used basis set of all possibles. Yes?
What does that index I represent in G?
So, yeah, well, there are different ones. So the capital I is which atom it is.
This one.
Lm is the angular one, and then you can have for each angular momentum, you could have in principle several radial functions, and I is this. Okay.
Okay,
So,
so it's just
so if you have heard about these things, people say Gaussian functions, they are double theta, triple theta. Well, this they mean for each angular momentum there are, for example, 2 radial functions or 3 radial functions.
It's just like N in the book.
Exactly. And here, so if you have several, they are distinguished by different alpha. So the alpha determines how quickly the Gaussian goes to 0, and therefore you can describe various radial behaviors of the functions.
Is that alpha naught or alpha sub I?
Alpha sub, where I should have written alpha sub I, to sum over, well then I cannot put it here, let me put it here. Okay, so primitive Gaussian. Yes.
So while, because the atomic basis functions,
Yes.
they are generally, like while we are doing quantum mechanics, we think of basis as eigenkits or eigenfunctions of a certain observable. So in the atomic case, it's the Hamiltonian, but in Gaussian case, it is just a mathematical tool, or
It's just a mathematical tool. I will say you why they have such a big success. In fact, I will come to this, but they are not eigenfunctions of anything. They are just functions which are linearly independent, and we write our solution as linear combinations of them. They are not eigenfunctions of anything. Here you're right, these functions are eigenfunctions of the atomic Hamiltonian. The Gaussians are not eigenfunctions of anything. But, as I say, so they are much more used than LCAO, and this has a very practical reason. The fact is that when you write down your equations to solve, very often appear products of 2 basis functions. For example, you want to calculate phi star phi, as we've done it before. Okay? If you calculate phi star phi, you will have a product of basis function 1 times basis function 2. So everywhere, from calculating a norm to a matrix element, everywhere in your calculations, you will have basis function 1 times basis function 2. So the product of 2 basis functions. In this case, when you multiply 2 complicated functions which have a non-standard radial dependence, you have to do numerically on the radial grid always the integration. While a Gaussian function have the advantage, if you multiply 2 Gaussians, one with the other, even if they are not centered at the same atom, the result is a sum of Gaussians. And this is what makes them so extremely useful. You can imagine that there are thousands of tricks. The fact that the product of several basis functions again has the same shape as the basis function themselves. And this is precisely because if you multiply e to the minus alpha r squared with e to the minus beta r squared, you again find something e to the something, but again it's always the shape of something r squared. Okay. So in the end, products of Gaussians again are Gaussians, and this simplifies a lot the equations which appear, and one can do many calculations analytically, and therefore it's very fast. Okay. So Gaussians are very popular. In fact, the most used basis functions, they are very popular because they are practical, and the reason is many analytical solutions exist. And also linked to this is the fact that products of 2 Gaussians is again a sum of Gaussians. Okay, so once you know how to handle Gaussians in the computer code, you can even handle their product, you can handle everything, and this makes them so popular. In fact, the most popular electronic structure computer code, which uses this basis set, has the fantastic name Gaussian. Okay. So Gaussian is the most used computer code, mainly by chemists. It has been developed first by a scientist named Popel. Okay. So he has had the idea, was one of the pioneers of solving the electronic structure in a computer using this basis set. And because this became so useful and so on, he even won a Nobel Prize for this. So you can win a Nobel Prize for writing computer programs or inventing a computer with a very useful thing. So he got the chemistry Nobel Prize now 10 or 20 years back. But the Gaussian code still exists and is continuing to be developed. One can buy it, it's very expensive, but it's one of the codes which exist. In fact, very often, computer codes for electronic structure carry the names of the basis sets. Like here, the Gaussian code, the code which we developed here in Trieste is called PW because we use plane waves, PW. So, the basis sets, as I said, are really the building block for anyone who wants to solve electronic structure problems. So both atomic orbitals and Gaussians are always localized on the atoms, which has a lot of advantages because you can already imagine that the solution of electronic problems of two atoms close to each other, it will a bit look like what single atoms would have, just that it's perturbed a little bit. Okay? So the advantage is you need relatively few basis functions, respectively if you would have used as a basis set something which is completely general. But now there are also some completely general basis sets. One other basis set would be to say that P alpha of R is e to the I g times R. So in this case the index alpha is the vector G. So this is what I said, this here is the same kind of as simply using a sine or cosine function, okay? Everywhere in space. This is independent of atomic positions. So these are not basis functions which are fixed on an atom. If you move the atom, the basis functions here do not change. And obviously e to the ij, this is what one calls a plane wave. And as I've just said, our quantum espresso computer code developed here in Trieste uses plane waves and it's called PW. So you can imagine you have in space something and then you can write every wave function as a linear combination of these, of a very broad wave function. So changing G changes the wavelength, and every function you can imagine, every shape of a wave function, you can write it as a linear combination of those functions, always. So it is super general. And you can also see the larger the norm of this vector G, the faster they oscillate in space. Okay? So there's one oscillation whenever this argument here increases by 2 pi. Okay? So e to the I, if you go by 2 pi, you have made one oscillation. So if G is very, very large, you move very little in space for one oscillation. If G is very small, you have to move large in space until the product G times R requires 2 pi. So by the norm of G, you determine how quickly in space these things oscillate. And finally, there is one last way of defining it. P alpha of R could simply be the opposite of this. This here is non-zero everywhere in space, and the opposite is you take a function which is always localized at one given position in space. And alpha in this case would be all those positions, and these positions are on a grid. Okay. So this is something you imagine in one dimension. You have space, for example x, and then you define a grid of points, all in equal distance, and your wave function phi, if this here is your wave function which you would like to describe, you describe it with its values on this grid. Okay? So the C alpha, what you keep in the computer, is the value of the functions at each grid point. And this, if you want the basis function, in this case, are basis function, delta functions centered here, 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 and so on. So this here is called a regular grid. And also this here is not atom-centered. So you might have an atom here, you get a given grid, and the grid is completely independent if your atom moves from here to here. Okay? So you have always this grid of points, like you have on your sheet, you have the grid points of your small, okay? And at each point of a grid, you save the value of the wave function. It's completely independent of where your atoms are. While if you write your wave functions as a linear combination of something atomic, then as the atoms move, your basis function changes. These here are independent. You can also imagine that these basis functions here, the plane waves, and the grid in real space, they are very closely linked. Because if you do Fourier transform from real space to reciprocal space, you end up here. If you go from reciprocal space to real space, you are here. So grids in real space and plane waves are closely linked, and every plane wave code does some part of the calculation in real space on the grid. Every grid code goes sometimes via fast Fourier transforms to plane waves to solve some of the part. So these two things are always linked. If you use plane waves, you also use grids. If you use grids, you use plane waves. Okay? So all these functions are there in order to be able to store in a computer a shape of a single particle wave function. Okay? So what we store in the computer are the expansion coefficients, because we know, the programmer knows, that the first expansion coefficient corresponds to that shape of a function, the next to the other shape, and so on. So now we have defined all this. And then, where is it? And I would like to mention one thing of Gaussians, which I've forgotten to say. So as I've said, Gaussian looks like this here, and then it goes to 0. This is a Gaussian. And so e to the minus alpha r squared. Okay? Alpha being large, meaning it is a narrow Gaussian. Alpha being small, it is a broad Gaussian. However, think about how you solve the hydrogen atom. Did the radial wave function look like this? The radial wave function which you found out had a different shape. It was not e to the minus. Huh? The atomic wave functions we find have the shape e to the minus, how shall I call it, sigma times r. Remember, you found solutions which are e to the minus r, not e to the minus r squared. So a function which goes like e to the minus r, it is also kind of something, and then it goes to 0, but it goes to 0 more slowly, and especially it has here a finite slope. There's a finite slope, and then it goes somehow to 0, like this. So, like in the hydrogen atom, in fact this is true for all atoms, atomic wave functions have this shape here, e to the minus something times r, and this is not called a Gaussian shape, this is called a Slater type atomic wave function. Slater meaning it goes like e to the minus r. Why am I insisting on this? Because this fact here that you have a finite slope when you go towards 0 with respect to a Gaussian which has always a zero slope at 0. So the derivative of this here at I equals 0 is always 0. The derivative of this here at I equals 0 is finite. Okay. So, but now we are in 3 dimensions. So in 3 dimensions there is something like a cusp at the nuclear position. And this cusp, meaning that you cannot take the derivative, this has important consequences. One can elaborate on this on the expectation value of the kinetic energy. So this, because the kinetic energy is linked to the derivative. Okay? So intrinsically, whenever people use Gaussians, and many people use Gaussians, they always have this problem that they do not get the cusp condition right. So when you hear people talking about cusp conditions, it means that they are using Gaussians, but they are losing the cusp close to the nucleus. In fact, you are also using this cusp when you have grids or plane waves, because these functions are also smooth. Okay, so you cannot represent something which is not differentiable very close to some point. So all these basis sets, except if one uses atomic type wave functions, lose this kind of non-defined derivative at the origin, which is for certain aspects important. So this I wanted to add. So now imagine we have chosen some basis set which we want, and now we can also deal with operators. Okay. So for example, representation of operators now. So because we have a Hamiltonian, the Hamiltonian has kinetic energy and so on. So for example, let's have a look at the kinetic energy. Kinetic energy of the electrons, TE. We know that TE, the operator, is minus h bar squared divided by 2m, the second derivative. So what one does now is one calculates that operator, but also the potential, all operators which appear. One calculates matrix elements between the basis functions which we have. So with a basis function, you calculate the operator and another basis function. Okay. Formally, this is then defined as minus h bar squared divided by 2m. You integrate over all space the basis function alpha of r star, second derivative, the basis function. Okay. So you take the second derivative of a basis function, you calculate the scalar product of the result with another basis function, and this here gives you the T alpha beta, a matrix element between the basis function alpha and beta. And the same you do with all operators. So you have a potential energy. If you have a potential energy, you also calculate this matrix element. You will have one basis function here, the product with the potential, another basis function. This will then, for example, give you the external potential between basis function alpha and beta, and so on. All your operators which you're interested in, you can write them as a set of matrix elements between your basis functions. Yes.
In the basis that we have used,
yes,
at least like 2 of them, I think the plane wave and the atomic one, they have infinite basis. So it will be infinite matrix. How do you think?
The basis functions which we use in practice must always be finite, okay, not infinite. This is, thank you very much, I should have said this earlier. So yes, you're right, there is an infinite number of atomic basis functions. There's an infinite number of plane waves, because you can choose any G which you want. In principle, there's an infinite number of points in a grid. Okay? So in principle, these functions can be infinite. But for anything you can handle on a computer, you must set a finite number. Okay? So for example, if it's atomic wave functions, one decides, I need a precision only to have 2 radial wave functions for every atomic function and angular momenta S, P, D, verbs F. Okay? And then if you want to be a better calculation, you say, okay, I say angular momenta S, P, D, F, also G or something. Or I take 3 radial wave functions and so on. So you can make more and more basis functions to make a better calculations. But the total number must be finite, because otherwise nothing fits in a computer. Okay? So the goal is always you can solve these equations only on a computer. So you must have a finite number of basis functions, from 1 to n. So typically you have many more if you have plane waves. The way how you, for example, for atomic functions, I just said, like for Gaussians, you choose how many radial functions you want, up to which angular momentum, and the number is finite. Okay? For plane waves, how is it done? Well, if you choose g's which are very, very large, as we have said, then the wave function becomes smaller and smaller. But we assume that our orbitals which we want to represent, they will not change on a very narrow scale. So one fixes a maximum length of the g vectors and takes only those g vectors which are smaller. So this is the way how in plane wave calculations it is. In real space, it's the same. One doesn't take an arbitrarily narrow grid spacing, but a finite grid spacing, and this makes your calculations finite. Okay? Yes?
What is the essence of using different basis functions, B alpha and B beta?
Yes. So now, because in the end, what you would like to solve is some Hamiltonian times a single particle wave function is some energy times a single particle wave function. Something like this will have to be solved. Okay? So, however, in a computer, how can we do it? Well, we write this here as a linear combination. And we write this as a linear combination of basis functions. And we write the Hamiltonian precisely in this way with matrix elements. Then such a Schrödinger equation here becomes a matrix equation in the way which I will show you now. Okay. So, if you take all elements which are in the Hamiltonian, like kinetic energy and so on, you have one matrix for the kinetic energy. And what is the dimension of the matrix? There are as many alphas as you have basis functions. So you have an n basis functions times n basis function matrix for this operator, for that, and so on. You sum all these matrix functions, and you have your Hamiltonian in the basis of the chosen basis functions. So your Hamiltonian, which here is an operator, becomes matrix. A matrix of numbers. Okay? So this is an operator. But the scalar product to the left with the basis function, to the right with the basis, this is a number. Okay? And the set of all these numbers, T, gives you a matrix. So, and this is how we can handle it in a computer. A computer can only deal with numbers. It cannot deal with operators or something. So, what you do by introducing basis functions is that you go from a notation where you have operators acting on wave functions. You have a matrix of numbers acting, and now also this phi here, because this phi is C beta times the basis function B. So you will have, these are the unknown C's, these are the numbers here, is energy times C alpha. Here you will have a sum over beta. So this here is now a matrix eigenvalue equation. You have a matrix H, you have a vector of the dimension of the number of basis function you have, here with the same vector. So you have a matrix times a vector is eigenvalue times a vector, and you just have to solve, and this a computer can do linear algebra with numbers, and it diagonalizes a matrix. You had first the question?
Question would be, so the idea is that numerically when you implement this, you evaluate it at each value of R. So you have
Yes.
various sets of matrices
Exactly.
R's.
Yes.
So what determines, because I mean the wave function will be always finite.
Yes.
So
So
what
the calculation is always done in the box. Okay? You have always a finite box into which you put all your atoms. So your grid, for example, you leave on a grid in a box of a finite size. And then it depends. If you would like to calculate a molecule which is only inside the box and nothing outside, then you can choose as boundary conditions at the end of the box so that everything goes to 0. Or if you would like to calculate, for example, a crystal, then you can say, okay, my box is by 1 unit cell of a crystal, and I apply periodic boundary conditions. And And then I just must be careful, because I know from solid state physics course that the wave functions are not periodic, but there's loss theorem. So you then write as linear combination of the basis function the periodic part of the block function. And everything is so all computations always start with choosing a box into which you put your atoms in the system. You say, okay, in a crystal it will be periodic boundary conditions. If you have not in a crystal, then it's not periodic boundary, but for example, zero boundary conditions. And then inside this box, you choose a finite number of basis functions and write everything as linear combinations. And this brings you to having this here. Let me write again. So if I say that phi alpha is the sum over all kind of functions beta of ci beta times b beta of r. Okay, so this here is my phi. I have to act on it with the Hamiltonian h. Okay? Now I multiply this here from the left with another wave function, or with another basis function b alpha of r. Then this here becomes sum over beta. I have complex conjugate b alpha of r h b beta of r times ci beta, and this here is precisely the matrix element which we have given h alpha beta, if you choose to integrate over space. So this is where it comes from. You have h times c, and then on the other side you have simply e times your wave function is e times ci alpha b alpha. Okay. Then you multiply this also and you integrate. So here you have b alpha complex conjugate of r. Since it's known, this here is 1, and here you have c e times c. Here you have h times c.
Excuse me, sir.
Yes.
If we are taking a finite basis,
Yes.
And by taking a basis of a certain well-known problem, how do we ensure the completeness of that basis set?
It is never complete.
Okay.
So this is precisely one thing. So you have always a finite basis, and the finite basis is never complete. So you have always, in any kind of calculations, you will always have to check convergence with respect to your basis set. It's never complete. So you choose one finite basis, for example, you choose one grid spacing in your box, you get some result. Is this good enough? You only know if you choose then a smaller grid spacing, more complete basis, still not complete, but more complete. And if the result does not change, then you know, okay, this is good enough here at convergence.
Or maybe do we sometimes do something like this, because we know something about the problem.
Yes.
So we know the structure of the wave function that we want. So we choose specific things from our
Exactly.
set.
This is precisely this. If you choose as basis function, atomic kind of wave function, this is because you know of the solution, it will more or less look like this. And for this reason, you get away with rather few atomic wave functions. If you use grids or plane waves, you do not use this additional information that you know that the solution will look like atomic functions around your atoms. And for this reason, you will need many, many more here. So in the case of plane waves or this, the basis sets are easily 1,000 times larger than the basis sets you use if you have atomic orbitals. But the basis sets are always finite and they are never ever complete. But there is always a systematic way to make it more complete. By choosing more radial functions, by going to higher angular momenta, by using a smaller grid spacing, by allowing the G vector to become larger, you can easily increase the number systematically, easily increase the number of basis functions. When you increase it, you know your calculations will be better. And then you compare for various degrees of accuracy, and if your result does not change anymore, then you can be happy. Okay, so convergence testing. So for someone like me who does this kind of work, convergence testing is half of the time what I'm doing. So we get some results and then we test convergence here and there, and there are many things, and all this must be very well controlled. And you won't believe how many scientific publications you find which are simply wrong because people have not carefully tested for convergence of their result. Because obviously everyone wants to do more complex systems, more interesting things where some very fancy chemistry or some very fancy reaction happens. So one wants to do more complicated stuff, but the more complicated the things are, the more expensive it is already with a small basis set. So then going to complete convergence, one tries to avoid it, and often the results are wrong. Okay, so this here is how we go for if the Hamiltonian is a single particle Hamiltonian. In this way we go from an eigenvalue equation to a matrix equation. Okay? And this we can deal in a calculator. So for single particle Hamiltonians, this is going from operators to matrix representation. So for your computer, a Hamiltonian is a square matrix. And the dimension of the square matrix is the number of basis functions which you have chosen. Good. So now we know how we want to write the single particle orbitals which go into our Slater determinants. No? Now comes the funny thing. How many different single particle orbitals can we write? How many? Different orthonormal single particle orbitals are there. So how many of these phi I are there?
It has to be more than the number of particles.
Yeah, obviously it must be more, many more. Well, the answer is very easy. If our basis functions are linearly independent, which they generally are, then it's the number of basis functions. No? The answer is NB, the number of basis functions. Okay? So since the basis functions are not linearly dependent, we can make out of NB single particle functions, we can always write them into NB orthonormal single particle contributions. Okay? And now this here, the fact that we have in principle NB, and normally this NB is much larger than the number of electrons we have. So typically you need a typical calculation between 50 and 100 basis functions for an atom. But an atom has, if it's a larger, it has perhaps 10 electrons or so. Okay? So there are many more basis functions in our systems than electrons, which is normal because we have to allow our wave functions to adapt to the problem at hand. So we have to allow for a large variational degree of freedom for the wave functions, and therefore we need many, many basis functions to be as general as possible. So NB is always much larger than the number.
Theoretically, NB equals to NE would also do that.
Then you can write everything would be well defined, but you would certainly get a very bad result, except if you use as basis function something which you already know is the solution. But in principle, you get a very bad result, because you must allow your wave functions to adapt its shape. Okay? For example, you have one atom here, you approach another atom, certainly this will change the wave function of the electrons here, and in order to be able to describe any shape, your basis must be very, very, very general. We will see now an example. So the point now is that this fact that we need many basis functions for NE electrons, this is what leads us to the fact why electronic structure calculations are so difficult. So let us now look at the complexity. Complexity of many electron wave functions. So why is everything so complex? We have NB single particle orbitals. We know the many body wave function is a sum of Slater determinants. No? For each Slater determinant, I choose out of the NB, I choose NE orbitals, and I plug them together in the determinant. Okay? So, my total many body electronic wave function of x1 to xn will be a sum, how did I write it? About L, alpha L of Slater determinants L. Okay? So this is the most general many fermion wave function I can write for n electrons. It's a sum of Slater determinants. Each Slater determinant is what we see before, and an expansion coefficient. So I have finished my work if I know what are the expansion coefficient alphas. Okay? So for a given problem, I choose basis functions. I have NB basis functions. With these NB basis functions, I have NB orthonormal single particle orbitals. And then I choose all possibilities to choose n single particle orbitals to make a Slater determinant. I build all possible Slater determinants. And then if I know what are the expansion coefficients in front of it, I know what is the many body wave function. Okay? So in principle, everything is well defined. What we need to store in the computer is these here, the expansion coefficients. So what is really your solution is determined by these alphas. So these here are alpha L, expansion coefficients in terms of Slater determinants.
Excuse me. One step below this, we also did something similar while expanding phi as that. So where do we get those coefficients? Oh.
Yeah. So if you take this here, you take all Slater determinants, then it does not matter how you put the basis function together in these. You just need NB of them. They need to be orthonormal. And then it doesn't matter. Because you have all possible linear combinations, they will be anyway represented here. So it doesn't matter. So once you've chosen your basis sets and then made them orthonormal, then it doesn't matter which shape the single particle wave function has. Because all shapes will automatically be represented here. The reason is, if you choose a different linear combinations of basis function to build these here, okay, this means that in the Slater determinant, these phi's which appear here will be linear combinations. And the Slater determinant where you have one of the functions being a sum of two others is the sum of two Slater determinants. It's again, it's a miracle again of the determinant.
The problem is involved here. That problem is also already in this.
Yes,
problem.
exactly. So if you solve for all Slater determinants for this number alphas, then you get the exact solution for the given basis set. And it doesn't matter which order of the phi's or so you choose. So you choose a basis set, you make it orthonormal, you consider all possible Slater determinants, and you are done. So now comes the bad news about all this. So we know exactly what we need to do. We know it can all be done in a computer, but now the question is, how many Slater determinants are there? Do we have? Well, the answer is as many ways of choosing NE single particle orbitals out of NB. No? So the answer is N Slater determinant is what one writes as NB choose N electrons. Okay, so the number of ways to choose NE elements out of NB, which is simply NB factorial divided by E factorial times MV minus ME. Okay, so you have, say, 20 Slater determinants, you have 10 electrons, and how many ways are there to choose 10 out of the 20? The answer is this, and this is unfortunately a large number. Because in the computer you will say for each of the Slater determinants you have to store one number. And now we will see how many these are in practice. So I think the best way to see this is by looking at an example. So we would like to calculate now the electronic structure of a benzene molecule. The benzene molecule is nothing particularly complex. Okay, benzene molecule looks like this. You have 6 carbon atoms. Carbon, 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 carbon. And every time a hydrogen attached to it. So this is C6H6. Okay. C6H has 12 atoms. And 42 electrons. Okay. Every carbon has 6 electrons. You have 6 times 6 are 36 electrons which come from carbon, plus the 6 electrons from the 6 hydrogens makes 42 electrons. Okay. So this is kind of not really a small thing which we might want to calculate. Okay. So now we must choose a basis set. Imagine we would like to solve this with a grid in real space. With the grid in real space, we take a very coarse mesh. We take 10 points in each direction. Okay? So we have, and grid is 10 times 10 times 10. Okay? So you put this molecule in a box. We say we represent our wave function with 10 points in each spatial direction. And you can imagine this is not very precise. Certainly we would need many, many more. But let's just work with this here. So we have 1000 basis functions. Okay. Or in other words, on a 10 times 10 times 10 grid, you have 1000 linearly independent single particle shapes you can have. 1000 basis function in space means you have 2000 spin orbitals. Because each one of them can be filled with an electron which is spin up, with an electron spin down, so you have 2000 spin orbitals. Still everything seems easy.
Can you explain, sir, again how this 1000 basis functions?
So I put my molecule in a box, okay? And now I choose some basis, as we've said. And I say, okay, I represent my single particle wave functions with grid points, okay? So, for example, a Fermi wave function which looks like this would be represented by its value here, 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 and so on. And since we are 3-dimensional, we need 10 points in one direction. The truth is we would rather need 100 points. But okay, let's say 10 points in one direction, 10 in this, 10 in that. So the total number of points is 10 times 10 times 10, 1000.
So phi of r.
Yeah, so every phi of r is defined on 1000 points in space. Okay? Or you could have said we use atomic functions, we use, I don't know, something like, I don't know, 50 on every carbon and 50 on the hydrogen, or something like this. So the order of 1000 basis function is a very small number for getting good results. Okay? So imagine with this, we have that 1000 basis function in space, means we have 2000 spin orbitals. Okay? So, and we know that there is no magnetism in such an easy molecule, so we have 21 electrons with a spin up, and we will have 21 electrons with a spin down. Okay? So, we have 21 spin up electrons. And in the same way, 21 down. Yes.
Is the system fermionic?
Yes, electrons are fermions. Yeah.
I mean, if you have the structure as a whole, 21 or 21 now,
Yes.
I'm thinking that they are supposed to log the fermionic properties.
Well, we are only interested in the electronic properties. The electrons are certainly all fermions. So the wave functions for 21 or 42 identical electrons must obey the fermionic exchange rule. So the question is not if the whole molecule of everything together has fermionic or bosonic character. This is not the question. The question is you have a wave function of identical particles. In this case, the identical particles are the electrons, and each one of the identical particles is a fermion, because each electron has a spin 1/2. Okay? Okay, so we have 21 spin up, 21 spin down. So we have to choose out of 1000 spin up, spin orbitals, 21. How many ways are there to choose 21 out of 1000? Well, the answer is we have, so we need to choose 21 orbitals out of 1000. How many are there? It's 1000 factorial divided by 21 factorial divided by 1000 minus 21 factorial. You put this in a pocket calculator and you will get no number because these numbers are too large, 1000 factorial and so on. But it is approximately, this here is approximately 1.58 times 10 to the 43. So we've only for the spin up electrons, we have 1.58, 10 to the 43 different possibilities of choosing 21 out of the 1000. So many possibilities for spin up. For every possibility spin up, we have the same number for choosing them in spin down. Okay? So the total number of determinants, total number of Slater determinants is this number squared. It's 1.58 times 10 to the 43 squared. Okay? Because for each selection you've done in the spin up, you have any possibility for spin down. So in total, the number of Slater determinants is therefore approximately 2.5 times 10 to the 86. So in order to store, therefore, the many electron wave function, and this is only the electronic problem, so in order to store in a computer the many electron wave function, you have to store in the computer 2.5 10 to the 86 complex numbers. Okay?
Please explain how you get the total number of this
This here? So you agree that for the spin up, I have 21 orbitals which I choose out of 1000, and I mean combinatorially this is this number. Okay. So now you do this in spin up, and you have chosen 21 spin up orbitals for your 21 orbitals. You do exactly the same for the spin down. They can do the same. So also there you have 1.5 10 to the 43. Now the total Slater determinant has any of the possibilities you found for spin up and any of the rows you have spin down. So the number of possible determinants is this number times that number. And 10 to the 43 squared gives you 10 to the 86. So still, I would like to show you how large this number is. And so we have not yet, so these numbers, in fact, one must find the optimal numbers to minimize the energy and find the eigenvalue. We have not even talked about this. We are just talking about storing a possible many electron wave function in the computer. Just storing it, not even trying to optimize it. Okay? So we have to store these 2.5 times 10 to the 86 8-byte numbers. Okay. So this means we have 2.01 times 10 to the 78 gigabyte. So many gigabyte we have to store in a computer just to store the wave function. Today's computer memories today, if you use them, they are typically 2 gigabyte per centimeter squared. Okay. So the chips in these computers, this is the typical order of magnitude. So for our simple molecule, we need to have a computer memory. So the computer well, you know, you have so many gigabytes, you know, per square centimeters you have this, so you know, can calculate the surface. So you would have a computer memory with the surface of 1 times 10 to the 68 square kilometers. Still, this doesn't say very much how much this is. However, if we compare it to the surface of the Earth, which includes all ocean and so on, so the Earth has a surface of 5.1 times 10 to the 8 square kilometers. So this means we need only to store the many-body wave function of a stupid benzene molecule. We need 1.9 times 10 to the 59th planet Earth. Planet's Earth memory. Okay, so I mean, I think this shows very clearly. Obviously there's no computer memory which has the surface which is as large as a whole planet. But especially no one will give us 10 to the 59 planets Earth surface only to store the wave. And so this shows you really why these fermionic wave functions are so complicated and such horrible beasts. Okay? So we have a whole course in this diploma program about electronic structure, because solving the problem is conceptually easy. The equations which we have, they're all easy. But we unfortunately know that our many-body electronic wave function must be sum of Slater determinants. We must optimize every Slater determinant in it such that we get these numbers here. But even just trying to store the numbers is impossible. And the reason is the incredible combinatorial number of Slater determinants we can have. And remember, I have just 10 points in every direction in space. And clearly, with this, you do not get a really very nice shape of the wave function. You should need many, many more. But then imagine how this number, I mean, the problem is this factorial here. The number of how you can choose the 21 electron, the 21 out of the several thousand functions. There are so many ways that you have so many possible Slater determinants that all hope is lost. Okay? So now, obviously I do not tell you this with the hope, let's go home, we cannot solve the electronic problem. That would be very bad. But very obviously, we need more approximations. We cannot just go ahead like this, do Born-Oppenheimer and solve the thing exactly. So there is no hope in doing this. In fact, one can do it for very, very small systems. You can do it. If you have a system which consists, for example, only of 2 atoms, and you use a very small basis set, then you can do it still with computers. And this way of proceeding, of writing all possible Slater determinants, and optimizing the prefactors of all Slater determinants, this has a name. It is called FCI. This method. FCI means full configuration interaction. So whenever this is doable, you should do it, because whenever this is doable, this gives you the exact answer. Okay? So for the given basis set, no further approximations, you get the exact result if you do FCI. But it becomes very, very, very quickly undoable if you increase your basis set size or you increase the number of electrons or so, because of this problem which we have mentioned. So full configuration interaction would be the gold standard to solve everything, meaning you take all possible Slater determinants and you optimize their respective weight in your many-body wave functions. If you can do it, it's even quite easy to program. The bottleneck is really the memory of the thing. So full configuration, whenever you read a paper and someone compares some result with the full configuration interaction result, then you know, this is an exact result for the given basis. Why is it called like this? So full is clear. Full because one takes all Slater determinants, therefore it's full. Okay, full. And then for the word interaction is because one considers the interaction between different Slater determinants. Now, don't ask me why chemists have decided that Slater determinants are called configurations. It has something to do with symmetry, okay, but so in principle when a chemist talks about a configuration, he means what we physicists mean by essentially a Slater determinant. Okay? So they take full configuration interaction as optimizing your wave functions amongst all possible Slater determinants. FCI, if you could do it, you would do it. Okay? So I think this is a good point to stop. Because now, next time, what we do is, we say we cannot do all these Slater determinants, we will use some further approximation, and then we can get meaningful results. Okay? So next time, I tell you something about Hartree-Fock, which is the first kind of important approximation to do it better. Any questions? Perhaps I switch off this.